All right. So thank you, Rishi, for the. All right. So thank you, Rishi, for the warm coverage of higher physics. And now that we have our context well and set, we are ready to go through the electronics applications that play a very crucial role in this field. First, to give a bit of motivation and how we're going to go through this, we will start with the general schematics of particle detectors and the modern version of it, followed by a excursion into how the front end electronics works, how data acquisition and data processing works, and then we'll dive deep into trigger circuits and what are they, why are they important, why do we care about them, and their technicalities. After which, we will then look at a very specific example of a trigger circuit setup because you will be using multiple triggers for multiple different parts of physics phenomenology in detectors. So we will look at the ATLAS experiment, which is one of the three experiments in CERN, the three being ATLAS, ALICE, and CMS. So we will look at the trigger setup for ATLAS up to its level 1 mu1 trigger and try to understand its significance for physics. Okay. Without further ado, let's get started. So the general schematics are it can be pretty elegantly summarized actually. So you have a detector, then you have some front-end electronics which is connected to the trigger and data acquisition in a loop because the trigger needs to coordinate between, because the trigger is mostly in simple electronics lingo, it is just a very effective form of a filter. Only that it's a little bit more complicated in its construction and a little more sophisticated than a naive bandpass or a low-pass filter that we have studied earlier. And after data acquisition, it heads straight to the computer host. This is the typical architecture of experiments. But I would also encourage that we look at the general schematics of the new architectural experiments. So the newer, the more modern ones have a detector, have an ADA, and they have a DSP followed to a computer host. Excuse me. So this is the modern structure, but again, hidden within the ADA and the DSP are just again these components, only that we don't have their analog counterparts. Instead, they're just uh, just full and full of microelectronics. And in fact, if uh, you recall the slides which Rishi showed you, you would have seen this large tower of just a circular structure, and that is just literally 6 stories of 6 floors of microelectronics, and that is the level at which CERN is operating in. But yeah, let's not get muddled by it. Instead, let's talk a little bit about front-end electronics. They're basically circuits that are directly connected to the detector. So let me just add that direct to detector so that we have this in the back of our head. And they can include various sets of things. They can include discriminators, preamps, time to digital converters, and so on. So basically, the preamps are used for signal conditioning, and they can be voltage, current, or charge preamplifiers, really depending upon what the specific front-end circuit is. Just to give a brief overview, the voltage preamplifiers basically they match the input and output impedances to the detector output and to the circuits that follow right after the detector. So they're basically trying to ensure that there's no signal loss. The key aspects are basically just gain, noise, and bandwidth. They're very similar to our regular op-amp apps that we've studied. So they are those amps. The current amplifiers behave very similar to these ones, but instead they take current as the input, and the charge amplifiers integrate The detector output and the output signal of the charge preamplifier is also a kind of integration of the input signal. So if you are getting the input signal, you just take the integral, see if it has a correspondence with the components that it needs to flow to. If not, we have to step in here and do something. We have to either amplify it, or we have to sort of diminude it a bit. And again, the rise time is a very interesting quantity that we often talk about. It's the detector releases a charge at the end of the day, and uh, yet again, the issues with the rise time and with everything else are noise and sensitivity. And when I talk about sensitivity, I mean the ratio between the output voltage and the charge input. And to put into perspective, sensitivity is is dimensionally defined as voltage per coulomb. So yeah, and I mentioned that there's something called a discriminator, and well, let me just put it out here. So discriminator. So it discriminates, but what does it discriminate? Well, to put it very simply, they basically compare a signal with a threshold, and they sort of assert their digital output when the signal exceeds the threshold. It's basically you can colloquially call it a limiter. So you have a level above which it's chopping your signal up, signal down. Sorry. And usually these circuits have something called a one-shot circuit, and what they do is these one-shots can be re-triggerable or not. So they can result in an output whose width varies with time or not, sometimes depending upon the threshold. And a typical sensitivity, if you want to talk about it, is few MV, which is marginally greater than the threshold. And this excess voltage is sometimes also called overdrive, and that's a very colloquial term, like overdrive, as in we might have heard about it in guitars and so on. So you're playing a guitar, and if you have a knob that says overdrive, that basically means you're turning up the voltage beyond the threshold. So that's what it is by analogy. So yeah, and obviously there are different types of discriminators, and the most common ones are called the leading edge or the double threshold, and the constant fraction one. So just to give a brief, the leading edge one is non-re-triggerable. It relies on the voltage that comes first, and it conditions the rest of the input as such. And the double threshold one has two different thresholds. So it's somewhat like a bandpass filter, only that it's a limiter with two different ranges. It's not it's not passing something, it's just limiting things beyond a certain place. And obviously, just like any piece of electronics, some bit of the signal obviously sips beyond this threshold, and that's what gives it this quality by itself. Constant fraction talks about the sensitivity ratio. And there's also these very interesting QDCs, which is charge to digital converters. So charge to digital converters. What they do, they integrate the current at their input during a fixed time, and they do basically a numerical integration with respect to the dimensions of charge. And it basically needs a gate signal to set the integration and set the integration time. And if the gate is active during that point, and then the result of the current integration is then converted and stored in a digital format, and it's read through the DAQ, which is the data acquisition system. So you see QDC, you go to DAQ right after. So we'll be using these quite a lot. So QDC is charged digital circuit, and DAQ is data acquisition circuit. And yet again, the important aspects, noise and sensitivity. And in this case, since we're also talking about something that's digital piece of electronics, your sampling, rate and your sampling, the number of bits is very important. So there's a very interesting characteristic that's called resolution. Basically, number of bits. Resolution equals number of bits. So yeah, and obviously you also have your conversion time. These are the factors that sort of matter. And a typical, if you want to talk about the sensitivity, it's less than 1 picocoulomb per bit. It's a pretty accurate piece of machinery. And the conversion time can range from nanoseconds to picoseconds. So, oops, seconds. So yeah, I'm sorry, nanoseconds to microseconds. So it will be nanoseconds here, and it will be microseconds here. Yes. Or the other way. Sorry. And then you have another set of things that are called TDCs. Let me take this card out. So your TDCs are time to digital converters. They basically measure the time elapsed between the start and stop of a signal, and this measurement is then converted to a digital format and read through and has the same set of characteristics. So resolution matters, conversion time matters, your sensitivity matters, your noise levels matter. And sometimes they can, again, it goes from here directly to the DAQ. So any piece of front-end electronics that has the word digital in it, it's going to go straight to DAQ after whatever processing it's going to do. It's going to go straight there. And an interesting fact about the TDCs are they can have multiple channels. They can be common stop for a set of signals, or they can be common stop depending on how you configure the channels. And the typical sensitivity is pretty similar to the QDCs, which is around a picosecond per bit, and the conversion time can range from, again, nanoseconds to milliseconds, and your full range can, for per component, obviously it can vary. It can go from 8 to 16 bits along those order, and the accuracy of these these microelectronics very much dependent on the method, the numerical integration method that they follow. So yeah, this is a quick intro to front-end electronics. Now we'll head to DAQ, which is data acquisition. I'm not going to talk about the very detailed technical aspects of data acquisition because it's a very complicated process. And the reason it's complicated, we'll see when we're talking about trigger circuits, is that in CERN, you have 40 million so-called events per second. And there is no computational facility on the planet of Earth that has the power to hold or even process these things. Gigantically huge amounts of data. And in fact, the CERN did invent the World Wide Web, the internet as we know today, but even then they could not handle the amount of data that was popping out of the machine. So we are left with the problem of what do we do? How do we deal with it? So the idea here is to then look for interesting pieces of data that we only care about. So this is where trigger circuits come in, which I'll talk about later. But logistically, the challenge is more with data acquisition here. So I'll talk a bit about it. Yet again, so what we do is we only look for interesting events by using filters and trigger circuits, and then in the data acquisition stage, obviously you can't process this serially, and if you did, it would be a nightmare. So you use different sorts of algorithms. I think sometimes the way your scheduling works in those systems, I think, might be based on round robin and different methodologies. But I will talk a bit about from the historical perspective. So this is not the exact modern viewpoint, but it will set up very beautifully for us the understanding of trigger circuits as we follow. So the DAQs that I'm going to talk about is serial chain, ironically, and they're used in what's called cosmic muon tracking, which is to say we are concerned with muons that pop up in our atmosphere from the cosmos. So these are particles that are coming from the universe. So we're currently in the realm of astroparticle physics. And in fact, fun fact, a few years ago, a few MIT students developed this tabletop muon detector that you can put in your pocket and carry around, and you would count the number of muons it's receiving at a given time. And you can then connect it to your laptop and basically measure the number of muons striking the surface and so on. Very, very simple, very elegant, very cost efficient way as well. Maybe I'll send up a link to that. But anyways, coming back to the DAQs. Uh, when I say DAQ in this context, I mean to the hardware and the software. It's not just one part, as we saw earlier as well with some pieces of the micro digital electronics. This means that there's some hardware connected to the front end, which acts as an interface, and then at the back end there is a connection to the host computer. So that's what the DAQ does. It's a bridge between the front end and the host. And in the 80s, there were these CAMACs and fast buses. So the CAMAC is basically an electrical and mechanical standard. It specifies what's called a crate hosting and a powering front-end card. So you had punch cards, and there's a very specific protocol for punch cards and controlling how things go from one end to the other end. You would then have crates that were controlled for the movement of these cards. The crate controller is connected directly to the host, and usually there's something called a wax, which is a VAX. Let me write this down. Actually, so you had a CAMAC, which went to a wax, which is a digital crate control. And this CAMAC DAQ basically transfers 24 bits roughly in a microsecond, that is, and it's non-bidirectional, which is to say that when the CAMAC was used, you had a TTL bus that goes this way. That's it. There's no there's one way, and it's the highway for the CAMAC. And the other case, the fastbus DAQ, well, the CAMACs were preferred over the fastbus because they had better life, to put it succinctly. But if you dug deep, you'd know that they were made of a different unique set of hardware which relied on vacuum tubes and so on that were replaceable and thus had a longer life. But the fastbus had a shorter life but it was a great enhancement because it had what's called an ECL bus, and it could host pretty sophisticated crate controllers, and these were based on pretty sophisticated CPUs, and they could be directly connected to disks, and it was advanced. But again, the fastbus had again, with any piece of industrial electronics, the worst scenario happened to the fastbus: low life, expensive. So when they were building the LEP, the linear collider at CERN first, they were using the CAMAC. They shifted to the fastbus, and they went back because it wasn't sustainable for them. But they did make some innovations. So what they did was they used a military standard protocol called the VME, and that allowed them to transfer around 32 to 64 bits. So the distinction between the CAMAC and the fastbus is not the number of bits it's transferring, but the fastbus has better crates or crate control, as they say. but they both had the same number of bits being transferred per microsecond, 24 bits. But the VME gave people 24. I'm sorry, 32. Sorry. 32 bits. So yeah, maybe I should write this. Yeah, 32 bits. And but it was a military standard, and then like CERN had to redevelop it because obviously you couldn't just take it away from the military. And later on, there were various other DAQ standards that were developed, and after a point, it got to a stage where you could just directly use the Ethernet to connect to the host, and then that opened a completely new era. And the way it's done during data acquisition now is they have these uh, basements full of giant cloud computers, and it's a Ethernet cable that goes all the way down there. And it's a gigabit Ethernet. The most recent version is 150 gigabits per microsecond, which is just the fastest you could get, the highest transfer rates, because even losing one event would cost a lot because you're not capturing 40 million events. You're obviously this is when I say 40 million events, I mean in one run, and no experimental search is done in one run. You usually have 3 to 4 or 5 runs, and in fact, if you look at what Rishi said earlier, there was this diphoton excess, which was like a bump, but then as data came over, it wasn't a bump. So this usually happens when you have 1 or 2 runs, and this happens when you have 3 to 4. So there's a key distinction. There's obviously when you do more runs, your data becomes more averaged out, you get a better picture, but that's not the point. The point is, in one run, you're not looking at 40 million events, you're going to probably look at 20,000 or so. It's a very low number of events if you observe, and but it's per second. But again, that's the capacity at which we're running. Maybe in the future we would effectively be able to store 40 million events. It's more of a technological leap rather than a conceptual one, to be honest. Uh, but yeah, so losing one of these bits could be very, very devastating, and one of these events could be very devastating. That is why we use the highest transfer rates using Ethernet gigabit cable. And right now, they either go directly to disks or tapes where they can be held and stored for long-term process. Even though with tapes you have to go through serial processing, we still prefer it because of how robust it is. Or sometimes for preliminary stages, we do use digital ones. And now, armed with all this, we will dive right into trigger circuits and what they are. So a trigger circuit is basically the simplest method to suppress useless data and noise. The two greatest enemies to any high energy physics experiment: noise, background noise, and useless data. Because again, remember, 40 million events per second, not useless at all. So triggering is also the first zero suppression, which is to say that when there's a significant interaction, the trigger then signals the larger circuit. Then it goes to the front end, which captures the event. So the trigger is telling me, trigger basically tells me what's useful, and the trigger can answer this question for me. So the feedback loop is trigger answers if it's useful. So is it useful? And if my answer is yes, then I go to my front end, and my front end captures it, and then it goes to my DAQ and then DAQ to host. So this is the basic process in a nutshell. But there are quite many difficulties when it comes to trigger circuits. And what are they? So the thing is, this must be happened before you even register the event, as we'll see. So this has to happen extremely fast if you want the right set of events to be registered at the soonest. And because of that difficulty, usually what happens is your front-end electronics, so you'll have two parts. So your interfacing with the trigger would have analog parts, and your interfacing with the DAQ would have digital parts, right? So this is basically to lose as little as charges during the integration step. Therefore, the triggering circuit must be fast enough to prompt the capture. You remember, this is pre-capture, so it must be exceptionally fast. And it's also very similar to, for example, what happens in an oscilloscope working in the normal trigger mode. So, what happens in an oscilloscope? Basically, when the input signal crosses a threshold, so your input can go, let's say it's a square wave, and my square wave crosses a threshold, then my oscilloscope triggers the horizontal sweep, right? So this sort of results in a coherent. I'm sorry. This would be a rough picture of the AC input that the uh, oscilloscope is receiving. So based on this crossing a threshold, I would then swing this way and then this way. So this is basically triggering my output. But in this case, I'm triggering my input. It's not even an output. So it's a bit more complicated, but it's quite analogous. So in modern experiments where the event rate can be high as 40 billion events per second, there are not one trigger levels, but there are uh, n trigger levels. And sometimes you can have, as we'll see later on with the Atlas experiments, specialized trigger levels. Right, so these are specialized for each particle and so on. And each trigger level, basically what it does is it filters out a specific set of non-relevant events, and it signals to the bigger trigger levels. So it's more like triggers, and the way this would work is you have a small trigger, which then talks to a bigger guy, which then talks to a bigger guy, which then might actually blow the whistle for the front end to actually capture this event. So two good examples, things that we may have come across beforehand, are photomultiplier tubes. Photomultiplier tubes, yet again, are sometimes used in astrophysics as well for just capturing the night sky. Are these new pieces of photomultipliers that are called silicon photomultipliers, or SIPM, are used. So basically, there are two light detectors illuminated by scintillators in cases. So this, as we'll see in the next slide, uh, can get a relevant count rate, and the efficiency of these can also be sort of calculated, and we can count this in when we're actually trying to make a analysis of the data. So since there are multiple different kinds of detectors across the world, we also need to have a conversation about making the hardware transparent and open to the entire world and the physics community, so that when we're comparing results, we can actually say, oh, okay, this anomaly could have been a cause of such and such and so and so. So yeah, this is a simple example. So you go to the scintillator. The scintillator gives off light, and the light detector here is either a silicon-based photomultiplier or just a bunch of photomultiplier tubes. This then goes to the discriminator, which acts as a limiter. Cuts off, so this tells us exactly what frequency of light, for example, is necessary. So if my frequency of light crosses uh, is below a threshold alpha or nearly equal to threshold alpha, and then this gets triggered, and then this goes here, and this just regulates my voltage and current levels, and then I actually go to my counter, and this would go to my DAQ and back to my host. So yeah, this is the entire process. And sometimes, okay, let me actually go over the previous one. So two equivalent channels actually process this. So it needn't be a PMT or a SIMP, and it could be both SIMP and and PMT. Uh, and basically what we're doing here is we're doing an AND operation here. So this is a pretty simple comparator that we've placed here. So both of them say yes, both of them detect the same signal, and then go to the, then yeah. Otherwise, hell no. So this is the setup, and this is sometimes referred to as a coincidence circuit. Basically, it can accept double coincident events and reject single ones. And a double event is basically it happens when a particle hits a scintillator, both the a scintillator, and you might be wondering, or uh, how can one particle hit two scintillators? So remember, we're talking about quantum mechanical particles, so they are uh, not localized in space. And the reason they are not localized is centrally stems from the uncertainty principle. And let me tell you why this arises. Yeah. So the reason is because we're always talking about momentum conservation. And in fact, when Rishi was talking, he might have talked a little bit about transverse momentum. And in fact, when we're looking for new particles, we're looking where there's missing momenta, and that's how we're trying to discover mass. So mass is basically coming from the Einstein relation. So you find the missing momenta, then you might be, and under conservation of energy and momenta, you then might be able to create a relationship between mass and momentum. And then you might arrive at and say, oh, okay, this is the breast mass of this so-and-so particle, and so on. So to put it in a very simple lingo, so we want to know this very well. We want to know P very accurately. So our uncertainty would fling to X. So that's the thing. You can only pack your uncertainty in one place. So you can pack it here and or here. So another good example of this is the LIGO experiment, where they did something similar with lasers as well, to make sure that their phase stays uniform, so that they can actually observe something of a phase difference that is smaller than the atomic nucleus of hydrogen or helium. So yes, that is why you can have a single particle hit two scintillators. A very simple fundamental physics reason. And you might think this event is rare, but it can happen pretty much a bunch of times, and it must be accounted for. And although this is a naive case, it tells us a lot about what we're actually dealing with here. And in fact, you want to look at these coincidence events because it's more reliable to think of the coincidence between two detectors that were combined and put together in one place, rather than just one that was just lying around somewhere and then another one. So instead of running the same thing over and over again, I can be very confident of just a coincidence measurement, and then say, oh, okay, I've got this, and yeah, I'm cool with that. And again, if we start from this, we can sort of increase the complexity lots more. As we've seen, we don't have a single trigger, we have triggers. So that's what happens in this muon telescope case. Okay, so it actually uses several floors of detectors. So you have 8 levels of detectors, and then it flows the discriminator, which is through a giant AND circuit, and then you get the trigger output. Right, so usually these detectors are SIPMs, scintillators, or they can be anything. They can be the CMS things as well. So basically, in our case, we're looking at a muon, and a muon essentially crosses the telescope, hits a bunch of these levels. That can be tracked, and the muon trajectory can then basically, so if my muon is going to hit this detector with a certain intensity and hit, okay, let me actually sketch this out. So if I have, how do I find out the mu1 path is a good question. So if let's say my hypothetical path is this way, okay, uh, but you know, what I observe is a little more radical. So what I actually observe is, I observe high intensity here, a little bit lesser intensity here, and here is the least intensity. So I can actually conclude that, hey, my muon did actually take this path with the detector. So it's based on the intensities that we receive here. And from a digital electronics speak, how do I determine intensity? So if I was looking at the trigger output for a single event, it would be basically an AND operation. So if I'm looking at the AND operation, I want to know, if the AND operation here on average was more ones or more zeros. So which one's larger here on average? And when you compare that, you get that. Uh, and sometimes this also includes a tracking system that can actively sort of display the tracks. And this is the modern way of tracking things. So we're gone with the days of a where you just put some liquid alcohol in a glass chamber and you actually observe the particle parts using a camera or a very high definition detector on the outside. But instead, now we're looking at detectors directly, and we're sort of able to track the path. And we can make it a little bit more bigger than this yet again. We can look at what's called a combinatorial majority, which is to say that it looks for coincidences among multiple detector levels by using an AND port. So it's not a complete AND. So you can have an AND here, and then you have an OR here, as you can see. So you try to find out, hey, is my guy hitting all of these two? Okay, that's cool. I get a 1 here, I get a 0 here. That's still a 1. Okay, so it's a little bit subtle, but it's looking for the smallest coincidences it can find, is what it's doing. And so at a detector level, to put it technically at a detector level n, it's basically considered by the trigger and when the corresponding switch is turned on. But when it's not used, the corresponding input to the AND port is connected and is always kind of at active level. And what we've seen so far actually are sort of simple, naive examples of this combinatorial majority. And in fact, these are generally called combinatorial networks. But again, you can get more complicated, and to throw in a little bit of math in here, the major circuit usually has k inputs, and when the number of active inputs is and it actually outputs something. Your output is true if it's greater. Greater than some n input, some n sets of input. So here, in our case, we could say 3 because we've got a total of 4. Right? So it has you set some fixed n, and so there are obviously two different ways you can make this in digital or analog. And the digital one is a logic network that can be used, the traditional designs, and it's pretty similar to your K-maps that we construct. And the beauty of this is simplicity and speed. It's fast, reliable, and pretty simple, not so complicated. Your machinery would thus be more sustainable because easy to construct, and it's not going to be destroyed due to some one singular transistor blowing up or something. No reactive components, by the way, here. So this example here is k is equal to 4 and n is equal to 3 is what we've shown here. And basically means 4 AND ports and 1 OR port, but this is basically because k and n are small numbers. If you increase k and n, the number of AND ports increases as the combinations. And you can define this combinatorial majority combination Cn comma k as n factorial, sorry, n factorial by k factorial times n minus k factorial. So it's basically nc k. I'm sorry, kc. Yeah, nck at the end of it. Thus, when you increase k and n, you make the number of required AND gates too big for a practical implementation. For example, if you put k is equal to 10 and n is equal to 6, you'll require 210 AND ports. That's just nuts. And even if you use a very naive simplification of AND gates, if you say that, oh, I can just basically construct my AND gates out of some simpler set of gates, let's say XOR or some sets of gates that are readily available on the market, that are cheap and reliable and so on. And if you did do that, it does still get tediously complex, and your complexity can almost exponentially rise as the number of Ks and Ns goes up. And moreover, your N is fixed, always. Your N is always fixed. And this is not a good sign, because when you're making a detector, at the end of the day, you want some level of flexibility with respect to that particular experiment. You want the experiment to, in the physics sense, you want it to explore maximum number of phenomena. So you want your N to be flexible as well. There's a different way to build something, the exact same thing, but a different sort of strategy. Is you use something that's called random access memory, and that's just RAM. You just use RAM. Why would you use RAM? Well, it's basically used as a lookup table, and we call this types of circuits a magic box, and we use really fast ECL RAMs, and sometimes they're termed as, I think, DDR4s in the industrial terminology. They're so they're more flexible because they use flip-flops inside them instead of gates. And well, obviously, flip-flops are constructed out of gates at the end of the day, but not just gates. You're making a different entity out of those things. And you basically can program this, and you can program in coincidences. You can program in anti-coincidences, and you can construct a majority sum and so on, just for these combinatorial majorities. So this is the pictorial representation of them. So these are your input addresses, and this is your output data. So it's called a magic box schematic because you just have RAM here, and the RAM is erasable and programmable RAM. And I've not shown the programming logic because it's not tedious. It's just that we don't require it at this stage. We're only talking about the electronics. We're not concerned with it. But essentially what it does is it stores the data into the RAM cells, and the input signals basically have the address of the memory. And in return, the magic box outputs the stored value, and the addresses always correspond to a valid trigger combination. And so the only addresses that are stored are the ones that you have done your coincidence matching with, and that you consider to be valid. The rest are always set at 0. The rest of the address, the buffer is set at 0. And the required combinations for trigger can be done by pre-computing and sort of storing the RAM content and how you want the coincidences to be set up. It can be done before the experiment is run, and it's not done when you're manufacturing it, when you consider the previous case. And sometimes it uses current generators to power itself, and each active input is sometimes powered by the current generator, which might result in some excess current. But again, the excess current is directly proportional to the number of active inputs, and if you use a proper counter in one of the spaces here, you can effectively calculate the excess current to a certain degree and filter it out later on. Or when you send it to the discriminator, that would just lock it off accordingly. And the voltage, you could express this in analog using an analog majority circuit, and that is what we will do. So the current generator basically connects. All it does here, oh god, it's pretty shabby, but I hope this is not necessary. What's here is not necessary, but this pattern is more than enough. But all it does is it takes one summing resistor RS and it connects one current generator to it. So when you have RS larger than V threshold, you know, at the comparator point, then the comparator output becomes active. So you have your RS here, and if your RS is greater than your VTH, then your comparator, it becomes active. And for if you have a majority of, let's say, n inputs, you can sort of you can write it as the follows. So VTH must lie between n plus 1 times RS IC, where IC is just the input current, and it must be greater than n times RS IC. So all this is telling me is each active input increases the voltage on RS. I'm sorry, of the quantity RS by a quantity RS dot IC. But when n inputs are active, the voltage on RS results in Rn dot RS dot IC. And when n plus 1 inputs are active, it's n plus 1 times and so on. So the V threshold must be set between these values, and that's what we've done here for n inputs. And all this figure 10 is showing me is just a very simplified block diagram, and a real circuit can be done using what's called a positive emitter coupled logic. It's a little bit more complicated, and you're basically using coupled op amps along with a few transistors. And the advantages of this is that it can be used very quickly because you're using a current generator switch, and its design also avoids saturation since we have it grounded through transistors. So one example of this is as follows. So when you use the PC, when you use the PECL drivers, which is basically the positive emitter coupled logic drivers and long tails, the circuits can have an arbitrary number of n inputs, and you can also avoid the saturation by making the current flowing in the long tails to be chosen properly, and also by allowing it to flow to the ground. The voltage threshold range, you can change it according to your will, and the required number of active channels can be set again using a variable resistor for setting the VTH, and the pulses can be very fast. The rise time and fall time can be set accordingly, and these times are comparable with what's called the propagation time along the signal path. So your entire when I say comparable to propagation path, the propagation path is just the mean time it takes from the current to flow from one circuit to one component to another. And in this case, we're talking about triggers and your DAQs, sorry, your front ends and DAQs. So it's quite comparable to just letting the current flow instead of processing it as we should with the trigger. So that's pretty brilliant, right? And however, it does result in a few issues. So we must use something that's called transmission line theory, which is a mathematical model that the designer must use to implement proper impedance matching in order to avoid reflections of this signal, because it can flow that fast. And the last circuit that we'll talk about in this part is something that's called a mean timer. Let me get to it. And after this, we'll get into the analysis of graphs and so on. So yeah, the mean timer is basically they're used in many fields, not just in this context. But why they're used here is we want to obtain a mean arrival time. We're basically using it as the the Q TDC in this case, the time digital converter in this case. And the mean timer usually uses photodetectors, uh, which you have the same scintillator going to different photodetectors, and it can be used to calculate the point of incidence of the particle on the scintillators, because its output is basically proportional to the mean arrival time between the two input pulses. So you have two different input pulses and it arrives at this point. You can measure the time it takes from here to here and here to here. You subtract the time, you actually would measure the ratio between T1 and T2. So that's the idea that's going on here. We essentially want, okay, in this case, I'll say tau, which is T2 minus T1. This is what we're looking for. And in fact, we can simplify this a little bit more by means of waveforms. So here, more events are actually happening, and it's not just one. So the circuit uses a capacitor as a current integrator, and it basically integrates the two equal currents, each which are switched on by the input signals, and then the voltage across the ramp here is Vc, which is given by Q by C, and this is nothing but IC dot T by C. And the IC value actually doubles when both the inputs become active. And this is simply because the ramp slope changes. The total time which is required by the ramp to go beyond a fixed threshold, actually there's a linear relationship between the mean arrival time and the fixed threshold. So you can call, if you would like to call K the corresponding slope of the current of one generator, K is given by dVc by dt, and if you simplify this expression, you will just simplify. You will just get this guy, because you just sub in for Vc here. Vc you differentiate it, the T vanishes, and you just get IC by C. Yes. Now let's consider the T tot, or the tau in our case that we were looking for. You can call it T tot, tau, required to Vc for crossing the VTH. So you want your Vc to go beyond this at this point. So how does that happen? Whoops, let me actually go back here. Yes. So this time must be set to actually be equal to the for the light to cross the entire circuit length. So essentially, your tau equal to T tot. It's just this expression. So the VTH can then be, you can alter the VTH based on this K that we saw here. The K times T2 minus T1 plus 2K, and this is observed, and this is just your median right here. And this Tm can basically be derived by equating VTH to Vc. So you equate this to Vc, and you'll actually get a relationship. I don't want to go into the details, but you'll get Vc is equal to K tau. And that's what we were after all this while, because we would just want a linear relationship, and then things become easy to compute and process. So yeah, your result then is this tau, and the mean arrival time is tau by 2. So the circuit basically outputs a pulse after the double of the mean arrival time. And this is a pretty crude way of doing it, but you're talking about analog circuits here, and this is a naive example, so don't take this very seriously. And we're only setting things up so that we can explore them, and later on we can delve into the actual problems of why the mean is a pretty bad tendency, a measure of center of tendency, or why you could use a median, and why when you have sudden changes in the voltage, thus changes in T1 and T2, sudden extremal changes, your tau doesn't get affected by this. So yeah, and anyway, so we will then connect any of the output of the light detectors to a TDC, and we set the mean timer to output to its stop, and the resulting basically counts as proportional to the x coordinate of the incoming particle, and the waveform, the case of the particle, uh, here is actually it's hit exactly at the center if you observe this guy, or we assume it to hit exactly the center. And but you would get these three different waveforms. Instead, what you could do is you could superimpose them, and you could let it start and stop at these columns. And if the particle is in the left, the TDC counts the time of the waveform A, and if it's in the right, if it's in the second form, it counts B. If it's in the third column, it counts C. So you're basically using different sawtooths or different triangle waveforms for different positions of striking here, and you're only going to be looking at these means. And I know you could effectively just build up a square wave by summing multiple of these, or you could just use multiple small square waves and essentially look at the area. But again, yeah, we could do that as well, but here we're considering just 3 bands. Yeah, and so on. But there is a little bit of an ambiguity as to if it goes to the left or the right, or the center in that case. So what you do is you sample with the start of the signal, so you get the status of the other input as well. And if input B arrives before input A, the output is active here in this region. Therefore, the particle is on the right side, and again, it's simply solved by the timing. And however, this is a very crude example of the triggers that I've shown here. This mean circuit timer. We do not use analog ones anymore, but I hope this has given us a good picture as to how triggers work. Because now we are going to be looking at something that was actually implemented in CERN. We're actually going to be looking at the trigger circuits in Atlas. Excuse me, if you will, for a moment. Yes. So, the Atlas, as I said earlier, one of the 3 experiments right there. And let's actually look at an overview of it. It's not as simple as the schematic as we saw earlier. Let me break down each of these acronyms. Okay, so all the Atlas has is it's basically an inner detector inside a solenoid magnet, and it basically has silicon pixels which act as the detectors, and these are called silicon core strips. So you see SET, silicon strips. These are your pixels. These are the pixels of this detector. Yes. And yeah, so and sometimes these are called silicon microstrips, and sometimes you use something else that's called the transition radio tracker, the TRTs instead of the SETs. But again, the TRTs are more specialized. I don't think we'll be encountering them. And outside this electromagnetic quote-unquote calorimeter is a hadronic one, and it's using that one is using scintillating tiles in its barrel. It has liquid argon in its end caps, and then you have a muon spectrometer. So we just saw the calo, and this is the muon, and the muons they use TGCs. What are these TGCs? These are called thin gap chambers in the end caps, and they basically also have something called a resistive plate chamber in the barrels, which are fast enough to be used in the level 1 triggers, as we see. So there are similar to the mu1 telescope, there are multiple levels over here, and we will primarily be looking at the level 1. And for precision measurements, we also use something that's called an MDT, and the MDT is nothing but your monitored drift tubes, and you use cathode strip chambers as well to form the innermost layer. Obviously, this could be less complicated if I just showed you the diagram. Unfortunately, it was not available to me. But the next image, however, should clear it up a little bit more. So yes, as you can see here, everything that we just talked about. So you have your calorimeter, goes to the preprocessor, and then it goes to the processor, CTC, and then it goes to the detector front end after that. And there's a beautiful feedback loop between these triggers, and sometimes this can go to your level 2 triggers, which are basically supervisor triggers. Basic one level double checks, fact checks to the other one. Well, before we go any further, I think it's worth mentioning why do we even care about all of this? It's a very good question. The reason we care about this is because we want to find out a bunch of the answers to a bunch of fundamental physics questions, and just to describe them. So I believe Rishi set up the standard model pretty beautifully. There's a symmetry in the electroweak sector, which is to say your electromagnetic and weak forces are one and the same at a particular energy level. So you can test that, you can probe that using the CERN, and you can also look for many new particles that are predicted by supersymmetry, and you can look for extra dimensions or even composite particles. And in fact, composite particles were the most recent finding in the last month or so, where we discovered that pentaquarks can exist. It was a pretty interesting story about that. But yeah, there's been very little success over the years on SUSY and extra dimensional searches to mention. Yeah, and without further ado, let's get much deeper into how these things work. So there's actually a very specific algorithm for each thing. So let me start with an overview of the trigger system and then go to the first level trigger algorithm, and to give you guys a okay, actually I'll do this now and this one after, and I think I can walk you through this one, and we'll go for this. So essentially, it's pretty self-explanatory as to how it does the job. So you have these array of calorimeters, and this is an electromagnetic one. And you have a hadronic one after it. The reason is, if your particle isn't stopped here, but it continues here, it's not a photon. This is not a photon. It's a hadron. It's a composite particle if it continues beyond this thing. So essentially, this isolates, effectively speaking, your electromagnetic realm of particles, and this isolates your hadrons. And essentially, your summing is done vertically and horizontally, and it's you're basically, this is a very small region. It's like it's a piece of microelectronics, so you must imagine how tiny it is. So you have and these are your triggers at the end of the day. Behind these, okay, so here I have something that's at one level, and here I have something, and then I have a combinatorial circuit that's sort of backed up. But even in here, before I even go to these combinatorial circuits, I rather, instead of integrating them, I do vertical sums because of the discrete nature of these bits, and then I compare them with the horizontal sums and then obtain an average, and then I can talk to my trigger, and then my trigger can talk to my DAQ. And this happens once for the electromagnetic realm and then for the hadronic realm. This is just a repetition of what I said earlier. This is the menu of physics coverage that the Atlas trigger system can do for us. You can do supersymmetry, you can do composite particles, and here there's been a lot of success. And this is the thing. Okay, so we saw what an electron or a photon could be. Your electron photon get trapped here. Your muons, on the other hand, would go for the outer realm. Your jet, what the hell is a jet? A jet is just a mixture of particles being sprouted out at one uh, thing. And one very good example of this is the so-called diphoton jet of the Higgs boson, and this is in fact how we found out uh, that the Higgs exists. So we basically measured these diphoton jets. We reconstructed their uh, transverse momentum, and we saw that it could be none other than the Higgs that produces this, despite the fact that the probability of this occurring was 20 to 10 to the power 6. So it took up a considerable amount of cleaning, and trigger circuits played a major role here. So yeah. And this is just the trigger menu. These are the different nomenclature for different sets of particles. These are the rates, and this is the cross section. So yeah, this is for high and low luminosity. So you can, but your luminosity is very much dependent on your circuit design. So it's not something that you can tweak. It's something that you can build and sort of increase over the lifetime of a trigger. You can't exactly twist it and turn it like the ends of our circuit. So yeah. These are the differential cross sections. Not really necessary, but I thought I would throw this plot here to give people an idea as to what actually happens when we're talking about things. So essentially, here we're talking about the cross section, which is to say the characteristic surface area of collision, which characterizes the particles which are colliding, and this is the transverse momentum. And so this is a plot between the transverse momentum and the particles that we would observe, and each one corresponds to a different process, as you can see here. But obviously, this is not a real process, mind you. This is not an actual plot, because in an actual plot, you would actually have these error bars that would tell you what's the distinction, between the background, the noise, and so many different types of errors. So your error bars would exist, which is also why when Rich was talking about things, we were only thinking of 5 sigmas, which is a pretty high standard. And the reason is mostly because of these error bars and the different sets of fluctuations that we can sort of poke through. This is a simulated one, mind you, and it was done in the software. It's called Pythia, pretty common bread and butter thing among high energy physics phenomenologists. You basically type in your process, you get your plot, you can get your cross sections out of the software. There are other softwares that do this too, like Find Rules and a few more competing softwares. But essentially, the job of a phenomenologist is to compute these processes and ask the experimentalists to do things and actually search for the bumps and so on. So yeah, and this is a good example of how the muon trigger is set up. This is a level 1 muon trigger. As I said, we'll stop here. But essentially, all it does is it has different sets of calorimeters. So if your particle is able to cross the calorimeter, it means it's of a specific characteristic. And obviously, you have your low momentum ones here and your high momentum ones here, because if you can only cross that threshold after point. And as you can see, it can go up to 15 meters in length, and this is more of a schematic rather than a more electronic one. And with this, I would like to conclude. I hope this was a very interesting venture. These are the sources we used. Please do let us know as to what you think. Thank you so much for this opportunity, and I hope this was as interesting and enlightening to you as it was to us.